Okay, so we know that like dissolves like, but what other factors can affect the solubility of a solute? There are a few. Some of them make sense. Some of them require a little bit more understanding. Let's take a look at some of them. For one thing, the structure. Okay, we have two terms that you want to make sure you know. Hydrophobic. Hydro meaning water, phobic meaning fearing. Water fearing. Water-fearing or hydrophobic structures are nonpolar. Nonpolar doesn't mix with polar water, so that would make sense. They're generally insoluble in an aqueous environment. Hydrophilic, meaning water-loving, these are substances that are polar or that can hydrogen bond and are very soluble. Here's an example of two vitamins, vitamin A, which is called retinol, and vitamin C. Now, vitamin A, most of vitamin A is composed of just carbon and hydrogen, and you should know that carbon-to-carbon bonds and carbon-to-hydrogen bonds are very nonpolar. There is a little section over here, a hydroxyl group, an oxygen bonded to a hydrogen, where there's some polarity there, but not enough to make this molecule very soluble. So vitamin A doesn't dissolve in water. Vitamin C, on the other hand, has a whole bunch of sections of OHs. And in biochemistry in general, the more hydroxyl groups you have on a molecule, the more soluble that molecule will be. Vitamin C is very soluble. The upshot of this is that vitamin A, along with vitamins D, E, and K, you don't want to be eating too much of them because they don't dissolve in the water of your blood and blood plasma, and they're not excreted. They tend to build up. They're soluble in fat, and so they build up in fat tissue. That can cause problems. In the case of vitamin A, retinol has a slightly orange color to it, and too much vitamin A leads to a very orange color to your skin, but can also lead to some serious problems. Vitamin C, however, is water soluble, and so if you eat more than you need of that, you can eat as much as you want. The excess will just dissolve in the water in your blood plasma, and will be excreted through your kidneys and through your urine. So you can't OD on vitamin C. That's essentially what that comes down to. Pressure is another thing that can affect solubility, especially for gases. The greater the pressure above the liquid, the greater the solubility of that gas. And this is governed by something called Henry's law. Pressure is equal to K, a proportionality constant, times C, concentration. Okay? In general, the greater the pressure of the gas above the liquid, the greater the concentration of that dissolved gas. Okay, this is one of the reasons that soda is bottled in such a way that there is pressure above the liquid. That's why when you open a can of soda or a bottle, you get that hissing sound. That's releasing the pressure. The carbon dioxide that's dissolved in the soda is at a very high concentration with a closed can or bottle of soda. When you release that pressure, then you'll start to see the carbon dioxide becoming undissolved. It'll start to form bubbles. Okay? This is in general with dilute solutions of gases. And the gas, we don't want the gas to interact with the solvent, because if it interacts with the solvent, then that changes Henry's law. Okay? So in general, we increase the pressure, we increase the solubility, and vice versa. So here's an example. We have a soft drink bottle at 25 degrees Celsius, contains carbon dioxide. The pressure is 5 atmospheres over the liquid. Assume that the partial pressure of CO2 in the atmosphere is 4.0 times 10 to the minus 4 atmospheres. Okay? Find the equilibrium concentration in soda before you open the can or bottle, and then after you open the bottle. And I have given you the value of K. K is equal to 32, and the units are liter atmospheres per mole at 25C. So K is given to you. Okay, so find the equilibrium concentration, the concentration of CO2 in the soda before you open it and after. Write down the problem and see if you can figure it out using Henry's law. All set? Let's take a look. So before opening, we're going to use P of CO2 is equal to K times the concentration of CO2. We're looking for the concentration of CO2, so we just rearrange that to partial pressure of CO2 over K. The partial pressure of CO2 above the liquid before we open it is 5 atmospheres. That's all there is above that liquid. And K is 32 liter atmospheres per mole. So that gives us 0.16 moles per liter. After we open it, we release that pressure above it. All that's left above the liquid is the atmosphere, atmospheric air. Okay? So Concentration of CO is PCO2 over K, but the concentration of the pressure of CO2 has dropped considerably to 4 times 10 to the minus 4 atmospheres, which is just the air in the air above it. And K is the same for carbon dioxide at this temperature, so we get to 1.2 times 10 to the minus 5th moles per liter. The difference in those two concentrations you will see visually by seeing the bubbles of CO2 come out of solution. Soda does not bubble until you release the pressure above it. So if you look at a bottle of soda before you open it, you won't see any bubbles. The minute you open it and you release that pressure, then the gas, concentration of the gas goes down and it starts to bubble. Now here's something you might remember from sophomore chemistry. The effect of temperature on solubility is pretty straightforward. First of all, you can dissolve a solute faster if you raise the temperature. The kinetic energy of the solute molecules speeds up, and it helps to kind of knock off these pieces of the solute, and it helps to dissolve it faster. But more importantly, the mass of solute that you can dissolve into a given mass of water also increases with temperature. For most solid solutes, there are a few, the ones in red here, sodium sulfate and cerium sulfate. Both of those actually, their solubility decreases with increasing temperature. They have an exothermic solubility instead of endothermic. They're unusual. Most solids, you increase the temperature, you increase the solubility, and you can see some have fairly shallow lines, meaning the solubility doesn't increase all that much, and some like KNO3 or sugar have very, very steep lines. By contrast, gases have the opposite effect. An increase in the temperature of a solution decreases the solubility of gases. Okay, so you'll get less gas dissolved in warm water than you will in cold water. You see that with soda. If you have warm soda, it will bubble more ferociously when you open it versus cold soda, which doesn't bubble very much. Similarly, you can keep soda from going flat longer by putting it in the refrigerator. You keep the concentration of carbon monoxide fairly high.